Let's talk about moment of inertia. When we just discuss about moment of inertia, we can say it is the same property which is analogous to inertia in rotational motion. Inertia is a physical quantity which we use in translational motion, because of which a body has a tendency to maintain its state of motion. Similarly, moment of inertia is a characteristic property of a body which is in rotational motion, due to which the body has a tendency to keep its state of rotational motion intact. When we talk about inertia, we can say it is denoted by the mass of body. If body's mass is high, we say its inertia is also high. We use it in Newton's law like F is equals to ma, or acceleration is F by m. This says if mass is more for a given force, acceleration is less, because acceleration denotes the change in a state of motion, that is velocity. So if a body is very heavy, its acceleration is less. That means for a given force, high inertia is not allowing the change in velocity at a very high rate. So we can say here, for a given force, acceleration is inversely proportional to mass or inertia of body. Similarly, when we talk about rotational motion, when we talk about moment of inertia, like inertia depends on mass of an object, moment of inertia depends not only on mass, but it also depends on mass distribution. This can be written as mass distribution with respect to axis of rotation about which the body will rotate. Like here we use F is equals to ma. The counterpart of force in rotational motion is, yes, it is torque, which we already studied. So we can write torque is equals to I alpha, which is the Newton's second law in rotational motion. So here we can write angular acceleration of body as torque upon moment of inertia, and here we can write alpha is inversely proportional to moment of inertia. So we can state as angular acceleration is inversely proportional to moment of inertia. Here alpha denotes change in a state of rotational motion, because state of rotational motion is given by the angular speed of a body. If angular speed is changing at a fast rate, that means the moment of inertia is low for a given value of torque. And if for a given value of torque, I is very high, moment of inertia is more, the angular acceleration will be less. That means the body is not allowing the change in a state of motion for the given value of moment of inertia. Now we will discuss the moment of inertia of a point mass in circular motion. Say if there is a point mass m which is revolving in a circular path about a given axis of rotation. So this is the axis of rotation about which this particle of mass m is moving, and say the radius of this circle is r. As we have just now discussed, if the particle or a rigid body is revolving, its moment of inertia depends both on mass of body and the distribution of mass. As being a point mass, it is located at a distance r at one position only. Here in this situation, moment of inertia of this particle is given as a standard result, we use the moment of inertia as mr square. This result we use for a point mass moving in a circular motion with circle of radius r. So moment of inertia can be given as mr square. Using this result, we can generalize it for a rigid body or an extended body which is rotating about a given axis of rotation. Let's have a look on this also. Now in sequence, let's discuss the moment of inertia of an extended body in rotational motion. Say we are having a random shaped extended body which is pivoted about a given axis of rotation like this, and about this vertical axis of rotation, say the body is rotating at an angular speed omega, and if we wish to find out the moment of inertia of this body, for this we consider an elemental mass dm in the body which is located at a distance r from the axis of rotation. Obviously, if the body is rotating about the given axis, this mass dm will revolve in a circular path of radius r. Obviously, different particles will revolve about the same axis of rotation in different circles. Here, if we talk about moment of inertia of the elemental mass dm is, we can write it as di, which can be written as dmr square. As we have just now studied, for a particle of mass m revolving in a circle of radius r, moment of inertia can be given as mr square. So, for the elemental mass dm, it can be written as dmr square. So, total moment of inertia of whole body is, this total moment of inertia can be written as integration of di, this integration of dmr square. You need to be very careful about this result. Whatever be the shape of body, correspondingly will apply the limits of integration, and we choose the elemental mass dm, and this is valid for all rigid bodies. Whatever be the type of rigid body, for a rigid body we can state, we can use moment of inertia expression as integration of dmr square if dm is an elemental mass which is located at a distance r. So actually moment of inertia depends on mass as well as the distribution of mass. For the same body, if we change the axis of rotation, the moment of inertia will be different because mass distribution about different axis of rotation will be different. So we can also write on a note that moment of inertia depends on location of axis of rotation for a rotating body. If we change the axis of rotation, moment of inertia will change.